Welcome back. Hope you're doing well. Today we're going to be talking about the range and kernel of some of the linear mappings that we've been talking about already. Now, we have seen ranges and kernels when it comes to matrices without even knowing it. Kernels are going to be equated to null spaces in what is to come, and ranges to column spaces. Essentially, range is going to be, like it is for a function, all of the points that your function can map to in its codomain range. Remember, for example, if you have a function going from set x to y, the way you might try and graph this is you might say, okay, here is our pictorial visualization of what x might look like, and here's what y might look like. And f is going to be signified by the mappings from points f into specific spaces over here. Well, let's say that this is the point 0. Let's say that this is the point 0 inside of the codomain. We're going to say that the kernel of a function, this part right here, that this kernel will be all of the points inside of x, such that if you take f of that point inside of x, you're going to get mapped to 0. In particular, when y is a vector space, we're going to consider 0 to be the 0 vector. We're going to be working with the 0 vector here. Now, the range, on the other hand, is going to be like this. Let's say that you've mapped all of your points from x over here to y, and maybe you still have some points over here left over. Then what we're going to call the range to be all of those points, this now being a subset of y, such that there exists an x inside of x, your domain spot, such that f of x is equal to your element y inside of the range. So we only take a look at the places that have endpoints of arrows inside of that space. So that's the same sort of definition that we would have for functions. But kernel is a very new and interesting space because now that we have these things defined for us, it's going to turn out that kernel and ranges have very specific properties that help us out. Let's start with two vector spaces here. And let's let L from V to W be a linear mapping. We're going to be talking about linear mappings here in this video. So here's our definition of range, a subset of your codomain space going into W, so you see here, such that W equals L of V for some V inside of your domain. The range of L we're going to be talking about as L of V. The reason we're calling it this is that V is our domain. And so if you plug in L of V, that means every element in here, right? L of V for any vector V inside of our vector space, that's going to give you your entire range. For all elements inside of this space, there is some V such that that element is L of V. That's what's meant by this function notation here. The kernel, on the other hand, is going to be a subset of your domain. And this is going to be the set of all vectors inside of that domain such that it maps to the 0 vector inside of W. So in particular, this is the 0 vector in W. Neat little theorem here to kind of help us see why linear operators are pretty neat here. The first one is that the range of L is a subspace of W. And the second one is that the kernel of L is a subspace of V. So both of these spaces are subspaces. You can see that if you add two things inside of a space of L, well, L of V plus W, for example, is equal to L of V plus L of W. So if you have two particular vectors that you'd like to see if they add together to still be in the range, so for example, if L of V is going to be some vector A and L of W is going to be some vector B, that is, if A and B are in the range of the a range of this linear operator, then what happens when you look at A plus B? Well, if you look at A plus B, then you know that you can write that as L of V plus L of W, which is going to be equal to L of V plus W. That is, the vector V plus W maps to the vector A plus B. And because of this, A plus B is also in the range. You can do the same thing with scalar multiples, thanks to the fact that linear operators preserve scalar multiplication. And hence you get that this is a subspace of your space. The kernel works the very same way. If you try and add two elements inside of here, both of which evaluate to 0 for your linear operator, then adding them would give you 0. We've talked a little bit about this when talking about homogeneous systems of equations a couple of days back. So we'll kind of bring back that example in just a little bit. For now, let's take a look at this linear operator going from R3 to R3. And that linear operator is going to be matrix multiplication. Let's take a look at what is meant, signified by all of these sorts of things. Let's take a look at the kernel of this space. Well, the kernel is going to end up being the null space of this matrix. Okay, so what we're going to do is say, okay, whenever L of XYZ equals 0, that's whenever all of these essentially x, y, and z values. Remember, this kind of makes your little x value inside of your matrix equation. So ax equals the 0 vector. We want it to be equal to 0. Well, these values, these vectors x such that ax equals 0, that's exactly what we defined to be the null space of the matrix. It's going to be all of those vectors x such that ax equals 0, something that belongs in the domain in this R3 right here. The range L R3 is the column space of the matrix. Well, why is this? We go back to the original equation. What all values are possible whenever I write things in this form? Well, it's all values that are possible whenever I plug in whatever I want for x, y, and z, as long as all of those are real numbers. That's exactly how we define the column space to be. The column space is all possible values that this can take on. It's the span of all of the column vectors in this matrix. So this kind of helps us connect these notions of kernel versus column space of each of these sorts of things here. Now, the range of L is spanned by the columns of this matrix. That's exactly what we have here. 1, 1, 1, 0, 2, 0, and negative 1, negative 1, negative 1. So it follows that L of R3 is spanned by, well, any vectors that we'd like to choose here, as long as there's we can go ahead and take out linear dependence relations if we'd like. For example, I could already see that this first and third vector are just multiples of each other. So I could throw negative 1, negative 1, negative 1 out if I'd like, and just keep 1, 1, 1. I could also scale 0, 2, 0 if I'd like, and just plug in 0, 1, 0. Since these two things are not scalar multiples of each other, this would be a very good basis for the range subspace that it gives me inside of R3. So I know that the range of this, L of R3, looks a little bit like R2, doesn't it? Because we can make the coordinate mapping work for everything to be in terms of R2. To find the kernel of L, on the other hand, let's go through and figure out basically how many zero rows we're going to get. That, first of all, that tells us the dimension of the null space of this. So we can go back to our previous ways of trying to figure this out. But once we go through and figure out the row reduction of this matrix, we get an equation like this, okay? Well, if we're trying to figure out where all of this is equal to 0, we could augment our matrix a little bit by plugging in zeros over here as a fourth column, right? This is exactly how we would solve the system of equations ax equals 0, is we try and see what solutions do we have to these equations. This first equation is given to us as x minus z equals 0, because here we have x, y, and z being the variables associated to each of these columns. So x minus z, those contribute their coefficients to this equation. And then also over here, we get y equals 0. So hence, we get an element inside of our kernel if x minus z equals 0, as well as if y equals 0. So it will follow that we can actually make a line out of each of these things. If y is 0, then that coordinate in the middle always has to be 0. But as long as x minus z equals 0, or if x equals z, then we're good to go there. So we could just say, okay, make it so that the spanning coordinate, or the generating coordinate for this line, is one where x and z are equal. So 1, 0, 1 would work, 2, 0, 2 would work, negative 1, 0, negative 1. The kernel of L will be spanned by any of these vectors, right? Or is the line spanned by any one of the vectors that I was mentioning before? Let's talk about differential equations for a little bit. Again, this time it's been a little bit of time. I'll explain this briefly, but I'm not going to dwell on it because we will be talking more about differential equations later on. But I do want us to see how differential operators, like we were talking about in our previous video, also contribute to the notion of range space and null space. But let's take the space of thrice continuous or thrice differentiable functions such that the third derivative of the functions here are continuous. So thrice continuously differentiable, or just 3 times continuously differentiable. Let's take that operator going into the space of continuous functions where this operator is like this. Well, they need to be differentiable 3 times, so we need to have a u triple prime inside of here. According to the theory of differential equations, no matter what you put over here for g of x, no matter what you put inside of that, as long as you put in initial values for what u of a, u prime of a, u double prime of a is, for some specific initial value that you want to plug in, some a inside of the real numbers here, then you get a unique solution for any g that you plug in for what this needs to be equal to. Remember, that's the element of the range inside of this. That is going to be your L of u. Notice that the left-hand side is this equation. So we're saying that g of x is our L of u from before. Well, for any L of u, you get a unique solution. What does that mean? That means that this is a surjective function. L is a surjective function. For any g of x inside of C of r that I'd like to have plugged in, there exists a unique solution for it. So it follows that this is a surjective function. Okay, well, is it injective is an interesting question. Let's take a look at what happens whenever I plug in 0 in for here for g of x. What happens if I plug in 0 for here? Well, now, first of all, I'm going to be looking at the null space of this function. Here, this would be the 0 function, and I'm saying that all of this is equal to 0 here. Well, let's take a look at what that means. If I take a look at the initial data evaluation of this, taking u of a, u prime of a, u double prime of a, this ends up being a linear mapping. Well, when I restrict it to all of the places where this is equal to 0, this turns out to be an invertible mapping here. That means that we could go backwards and forwards. First of all, for any g, there exists a solution, and there's no way to get a second solution such that this is whenever you plug in 0 here. That's where we're using uniqueness. There's no way to get two possible solutions for 0 here. So given that we specify B0, B1, and B2 and all of that sort of stuff, once we've specified all of that, we get a unique solution. So that means that it is invertible once all of those things are considered. That is, when we've restricted g of x to be the 0 vector, and hence when we are inside the kernel of this linear operator. Well, we had three choices of what we could have done in order to get an invertible operator. We had to specify B0, B1, and B2. So that means that each one is its own little spanning part of this, that spans this kernel. So B0 was a choice, B1 and B2. Our choices in those three things mattered, and they could have been anything. And because of that, the dimension of this kernel is 3. So we might go through and ask what functions give us the fact that this system of differential equations, what gives us that this is actually 0? You could go through and check that these three equations work, namely the 1 function, because the derivative of 1 is 0, as is its second derivative, as is its third derivative. When you plug in 0 for each of these, you get 0 over here. So that would be one potential solution there. E to the x also works. The derivative of e to the x is itself, so plugging that in for each of these, you would get 0. X times e to the x also works, so that's another one. You can check that these functions are linearly independent using the Wronskian that we were talking about previously, and hence the kernel of L is the span of these three elements. We know there's no more because these three functions are linearly independent, and we discussed why the dimension of the kernel is exactly 3. So this is a basis for this space. Now, general linear equations are written in this form. L of x equals b, where L is a linear mapping going from two vectors, and b is a given vector from W, and x is some unknown vector from V. So linear equations are written in this way. The domain elements from the vector space comes in, you pop out, you get an element of the vector space coming out from your output. The range of L is the set of all vectors B such that Lx equals B has a solution. Think of this as like our matrix equation from before. The range of the matrix A is all of the vectors B such that Ax equals B for some x, right? So A is like our linear operator here. You can think of it that way. However, we are generalizing this to not only have to work between the vector spaces of Rn and Rm, but in between arbitrary vector spaces, V and W. And the kernel of L is the solution set of the homogeneous linear equation when you plug in 0 for B. And that corresponds to something we were talking about in terms of matrices when we were talking about homogeneous linear equations back in the day. Now, in general linear equations, the way that we solve these things are going to look a lot like the theory that we developed when we saw differential equations for the first time. You may remember that the way that you solve differential equations, whenever you have L of x equals B, say, for example, this was some sort of differential operator, you had L equals some combination of derivatives all put together. Lx equals B, if it's solvable and the dimension of its kernel is finite, which is prone to happen whenever you have finitely many derivatives being taken, just like we saw in our previous example, then the general solution consists of the homogeneous solution and a particular solution. X naught is a particular solution for us that essentially helps us figure out what to do with the fact that this vector on the right-hand side is not necessarily 0. It kind of is the part that allows us to get this to be 0. However, anything inside of here, T1v1 plus TKVK, that is all solutions to the homogeneous linear equation, Lx equals 0. So why is it that you're adding these two things together? You may remember from differential equations that if you add L of x naught plus T1v1 plus dot 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 plus TKVK, well, if you break this apart into two pieces, you want this equation to be solved, right? You want L of this value to equal B. Well, you break it apart like this: L of x naught plus L of T1, blah, 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 TKVK. So this is all of that other stuff. This is all of these things put inside of here. Now, we know that this is a solution to the homogeneous equation. That means L of this value is 0. So this just leaves us L of x naught. And remember, this is what we said about x naught being the particular solution. This is the part that is equal to B. Now, if you get a part of this, your solution that such that L of x equals 0, you can always add that in thanks to the fact that this is a linear equation, right? You can break it apart and say this is equal to 0, so I don't have to worry about it. This L of x naught is the only part that has to be equal to B. That is what's contributing to our particular solution. So that's why the general solution looks a little bit like what we saw from differential equations. We're just tying that into a linear theory now of just talking about linear operators. Any linear equation like this can be solved as long as your dimension of your kernel is less than infinity. Namely, you can pick finitely many vectors such that this works. That gives you a general equation describing all possible solutions to this equation of Lx equals B. So let's go ahead and see an example of this in a space where we definitely have a finite dimensional kernel because we're looking at finite dimensional vector spaces. Let's take a linear operator, or in this case, I guess linear equation or linear mapping, going from R3 to R2. And let's take it to be described by this 2 by 3 matrix. 1, 1, 1 in the top row and 1, 2, 0 in the bottom row. Let's go through and try and make a solution for what this is. Let's solve the equation Lx equals B, where B is the vector for 3. So all put together, we're trying to solve this equation. What XYZ values could I be plugging in here such that the matrix times XYZ equals the column vector for 3? Well, what we usually do for this is we do make our augmented matrix and attempt to do Gauss-Jordan elimination on it. We take our matrix to be the stuff over here to the left of our dividing bar, and then we have our column vector over here on the right, and then we apply elementary row operations in each of these segue parts here. So you can see, for example, that what I'm doing is taking R2 and I'm subtracting R1 from it. So I have this, and then after I do that, I'm going to take R1 and I'm going to subtract R2 from it. So I'm replacing R1 with R1 minus R2 when I do that. So these are both elementary row operations. Once I do that, I get this sort of a system of equations after I've gotten it into what is reduced row echelon form. And now that it's in reduced row echelon form, I go back and remind myself, okay, what variables were associated to each of these columns? It was X, Y, and Z respectively. So I go through and I write that system of equations back in. X plus 2Z equals 5, Y minus Z equals -1. And so solving for X and Y in terms of my free variable of Z, that is the variable that is not a pivot column here, that gives me this system of equations. So that's what I'm working with. So to get a general formula for the system here, I get XYZ equals this equation, this vector equation. Now, this doesn't look like the formula that I had before for what a general formula looks, right? What's the particular solution? What is the homogeneous equation solution? Well, we need to write it out so that we're getting all the constant terms in one vector and all of the terms that have t in it on another side. If you do that, then here is our particular solution. This is x naught. This is a value you could plug in for L such that if you plug in 5, -1, 0 in for this vector, you get the thing you want on the right-hand side. You get the vector for 3. Now, -2, 1, 1 is special because this is a vector that helps us understand what our null space looks like for this matrix, or like we're calling it here, the kernel of this mapping. The kernel of this mapping, turns out, is spanned by the vector -2, 1, 1. That coming from the fact that these are the coefficients in front of each of our t terms in each component, respectively. So this is the vector that spans our kernel space. Indeed, if I tried to plug in -2, 1, 1 inside of here, then I would get that L of that vector, once I'm multiplying by this matrix, equals 0. So that means that any multiple of that would also be equal to 0. And it's interesting, in fact, that we did not find any other vectors that ended up spanning. There were no other free variables for us to choose or use from. We only got z, for which we plugged in t in order to get this equation. So that means that our column space has dimension. Well, let's check real quick. Let's not skip too many steps. Our kernel, or our null space, has dimension 1. And since there are 3 columns, we also know now that our column space has dimension 2. So we can kind of analyze our matrix thanks to this sort of Gauss-Jordan elimination. Well, that actually is it. I'm a little surprised that went so fast. But if there's anything that you're thinking about here, I would recommend going back and trying to remember the Gauss-Jordan elimination stuff that we've been talking about from way back when. And you might be able to see now that there's a more general form going on. Indeed, we're only using the fact here that L is a linear operator whenever we're making this theorem happen. We're not using the fact that we're talking about matrices by any means. We're only using the fact that this is a linear operator that happens to have the nice little property here that the dimension of the kernel is finite, so that its general solution, its kernel, can be spanned by finitely many vectors. That's all that we're using in order to make this theorem. So we have a particular solution, something we may remember from differential equations, and a solution to the homogeneous equation, and that's this stuff over here on the right. So neat little discussion here about kernel and range when it comes to these linear operators. But that'll do it for me today. Thank you so much. Have a wonderful day.